In this video, we're going to look at a liquid-liquid extraction problem for a multi-stage cascade. And to solve this problem, we're going to use the Hunter-Nash method. We won't derive that method in this video. We're just going to demonstrate how it's used to solve these liquid-liquid extraction separations. Let's take a look at the following problem, in which we have a feed of 40 weight percent IPA, 55 weight percent ether, 5 weight percent water, that's mixed with pure water as the solvent to recover the ether. Now we have our phase diagram shown here as a ternary phase plot, and we've collected the data from a source and we've plotted that here with appropriate tie lines. The goal is to produce a raffinate that has less than 3 weight percent alcohol and an extract phase that has at least 20 weight percent alcohol. We're given a temperature and pressure, and we're asked to calculate how many stages are required for this extraction. So let's write down what we know, what we're looking for in a picture of our system. So we're given in this problem 3 compositions but no flow rates. So we're going to designate our compositions in mass fractions. We're going to say XA is for our alcohol, XE for our ether, and XW for our water. We're not told what the other compositions are, but we do know in this system that for our raffinate and extract phase leaving, we're assuming that in each stage we reach equilibrium. So these values right here will be on our equilibrium curve. So I've drawn a schematic here to represent our stages. Our feed enters at stage 1, and then we'll go into stage 2, and what leaves stage 1 will be our raffinate from 1. We don't know how many stages we have, so we'll have little n and our final big N for the number of stages. So we know our raffinate leaving is going to be from the last stage. And so for our countercurrent system, we're going to enter the solvent in here. We'll say the solvent is S. So we have our extract leaving from stage N, our extract leaving stage 2, and our final extract leaving stage 1. So we're going to use this nomenclature as we move forward in solving our problem. We're not given flow rates, which means that we're probably going to have to assume a basis. We're also going to assume that the system operates isothermally, that any enthalpy associated with mixing is negligible. Since we're given our composition of our raffinate and our extract, using the Hunter-Nash method, we need to determine our solvent flow rate. Once we have S, we're going to plot these points on our ternary diagram. We're going to plot our feed composition, our solvent, our extract, our raffinate leaving, and this all helps us calculate what's known as our mixture point. So let's start with step 1 and draw these compositions on our chart. And since we're using a pure solvent, this is going to be all water. We could plot our feed by looking at 40 weight percent alcohol, and that's going to fall somewhere along this line. Then we could choose either of the other 2 points. So in this case, I'm going to choose ether. We're going to go to 55%, which is right between here. Where these intersect gives us our composition of our feed. Now our solvent's pretty easy. We're going to use 100% water. So we're just going to draw a point over here. Now our extract and raffinate phases have to be at equilibrium. Not with each other, but leaving the appropriate stages. So our extract has alcohol of 20%. So we know that's going to be closer to our solvent side. So we're going to look for where 20% for our alcohol is on our equilibrium curve. And that's right here. We're going to do the same thing for our raffinate on the other side. We're looking for about 3%. So somewhere around right here. So we have our 4 points. Now we could calculate the mixture point if we had flow rates for S and F. We know our feed enters our system with our solvent. So these 2 combine to create our mixture. This mixture also must be equal to what leaves the system, which is our extract and our raffinate. So we know that these 3 are on a line and these 3 are on a line. And we get that by using a material balance, and the derivation of why these points all fall on the same line is shown in another video. So what we're going to do is draw a line from S to F and another line from our extract to our raffinate. And where these intersect is our mixture point. So now we could read the composition of our mixture point and use this and our material balances to solve for a ratio of S to F. And so this would give us an idea how much solvent we would need per amount of feed to achieve this separation. Now that wasn't asked in the problem statement, so we don't necessarily need to go down that road. But just to point out, the one thing we can do is use the inverse lever rule as well, since we know that we could write S over F equal to the length from M to F over the length from M to S. And this gives us about 1.48. So we would need almost 1.5 times more solvent than our feed to achieve the given compositions that we're proposing. Now we could also use the inverse lever rule for our extract and raffinate, since we can then calculate the ratio between those two, and using what we know from our feed and solvent, performing our material balances gives us an idea of the absolute amounts of these two phases. So step 2 in this process is to determine our operating point. We're going to say it's called P here, and our operating lines. So what we're looking for is a point P. So point P is a solution to our material balances, and we know that these must be on a line as well as those points. So we could draw these two lines going through our points. So we'll start with our line that goes from F through E1, and we'll draw another line that goes between Rn and S. Where these intersect is going to be our point P. So the last step, step 3, is to use our tie lines and equilibrium lines to determine the amount of stages that we need. So we have our operating point, and we know that each line that goes through this point is going to include the passing streams. And what I mean by that, let's take a look again at our schematic. We know the difference between this stream and this stream is the same as the difference between this stream and this stream, and that difference is P. So that also means that E2 and R1 fall on a line with P, and En and Rn minus 1 would fall on a line with P. So the first thing we do from stage 1 at E1 is to follow the tie line, since we know at stage 1 we're going to get equilibrium. So we follow that tie line to the other side. So I draw a point on the equilibrium curve on the other side for our raffinate, and I'll label that R1. So we know that R1 and E2 are passing streams that fall on a line with P. So we'll draw a line from P to R1, and where it intersects on our equilibrium curve is going to be where E2 is. So then from here, we repeat the process of following the tie line from E2 to the other side where we think R2 is going to be. Now I had to interpolate here, so that's probably my best guess without doing our interpolation method to draw more tie lines. So again, we know R2 and E3 fall on the same line with P, so we draw a line to R2, and we can figure out where E3 is. I'm going to get rid of these lines just to make it a little easier to see. Again, we follow the tie line from E3, and you see this time we get to our Rn. So based on this, we've drawn 3 tie lines, or 3 equilibrium lines, for our stages, and so we would have 3 stages. Now it's possible that you'd want to zoom in on this, be a little bit more precise. The first time I did this, I actually got around 2.8, so you would have a fractional stage. So it's important to try to do your best to draw appropriate tie lines and not guess. Hopefully this gives you an idea on how to use the Hunter-Nash method to solve for parameters in a liquid-liquid extraction separation.